Energy can neither be created nor destroyed. It will always be conserved. That is the law of conservation of energy. But if that is the case, the moment we turn off a bulb in a room, where does the light energy go? Similarly, when we are alive, we possess energy. So what happens to the energy in our body when we die? Where does it go? And if conserving energy is an inherent property of the universe, why do we keep saying, save energy? These are just some of the many questions I receive about energy every day. It is not just me. What is energy? Is one of the most searched science questions on the internet. It might seem like a simple question, but many people do not truly understand the scientific meaning of energy. This is because the word energy is often misused in everyday contexts. For instance, you might hear statements like, "This bracelet channels positive energy to improve focus," or "The negative energy in this room is affecting your mood." In these examples, the word energy is not used in its true scientific sense. In physics, energy takes many forms, like the warmth you feel from sunlight or the motion of a rolling ball, but it does not have emotions or intentions. So, what exactly is energy? Does energy have positives and negatives? And what is the true meaning of the law of conservation of energy? Let us dive into these fascinating questions in this video. Hi friends, welcome to a new video of Science Simplified for All. In language, the word energy can have many meanings, but in science, the word energy has a very specific meaning. Energy is defined as the ability to do work, that is, the ability to cause action. So first, we must clarify what is meant by work. If a force is applied to an object, and as a result, the object moves in the direction of that force, then we say, work is done. The ability to perform this kind of work is what we call energy. For example, imagine you are trying to push a large box. If the box moves in the direction you are pushing it, we can say that work is being done. Similarly, if you lift a heavy object off the ground and it rises, work is also being done. In both cases, you are using the energy you have to do this work. This ability to do work is what we refer to as energy. But here is an interesting point. If the box does not move despite your pushing, according to the definition of work in physics, no work is being done. Similarly, if you are just holding a heavy object without moving it, physics says no work is being done because the object is not moving in the direction of the force. According to this definition, you are not expending any energy. But from practical experience, we know that if you try to push a box or hold a heavy object for a while, even if it does not move, you will start to feel tired. So it does not seem right to say that no energy is being spent in these situations. Let us consider this. If we place a sack leaning on the box, the sack also exerts a force on the box. It can do so for an indefinitely long period without using any energy. Similarly, if we place the heavy object you are holding on top of a pillar, the pillar can support the weight for years without expending energy. So, applying force alone does not cause work, and hence, in these cases, no energy is spent on the system. But when we do the same, we feel exhausted. The difference lies in how our bodies work. For us, to apply force on any object, or even to stand straight, various muscles in our body have to contract and relax. For this, muscles need a constant supply of energy. Additionally, our vital organs, like the heart and brain, are always working to keep us alive, which also requires energy. A pillar, on the other hand, does not need to do any of this. It can hold a weight for any period of time without expending energy. So even in situations where no movement occurs, our bodies still use energy because of the way our muscles function. However, according to the scientific definition, no work is being done. So technically, no energy is being used in the context of physics. This raises the question, where does the energy we spend go? The energy our muscles use to exert force is converted into our body heat, which is then dissipated into the atmosphere. What I'm highlighting here is that there are situations where our everyday understanding of energy might differ from the concept of energy in physics. There are many types of energy, such as thermal energy, chemical energy, nuclear energy, and electrical energy. However, the biggest classification of energy is into two categories: kinetic energy and potential energy. Most of the types of energy we mentioned earlier can be classified into one of these two categories. Kinetic energy is easier to understand. It is the energy due to the motion of an object. For example, a moving ball possesses kinetic energy because of its movement. If that ball hits something, it can use its energy to perform work like knocking over an object. That is kinetic energy in action. Potential energy, on the other hand, is the energy stored in an object due to its position or condition. Let me give you a few examples to clarify. When we lift an object off the ground, we are working against the Earth's gravitational force. The energy we use to lift the object is stored as its gravitational potential energy. When we release the object and it falls, this potential energy is converted into kinetic energy. When we pull the string of a bow, we do work against the force exerted by the bow. This work is stored as potential energy in the string. When the string is released, the stored energy propels the arrow forward. If we hold two magnets in a way that they repel each other and then force them closer together, we are working against the repulsive force between them. The energy we use is stored as potential energy between the magnets. When we release them, this stored energy causes them to quickly move apart. So whether we are working against gravitational force, elastic force, or magnetic force, the energy we spend is stored as potential energy in the object. When released, this energy transforms into kinetic energy. So potential energy is stored energy. The forms of energy we mentioned earlier, such as thermal energy, chemical energy, and nuclear energy, can be seen as variants of either potential or kinetic energy. For instance, the thermal energy of an object is the kinetic energy of vibrating atoms and molecules within it. When we burn fuel, the chemical energy stored in the chemical bonds of the fuel is released as heat. When we say fuel, we do not just mean substances like petrol and diesel. Energy is also stored in compounds like glucose and fat, which our bodies depend on for energy, and also in explosives like RDX and TNT. The energy in chemical bonds primarily comes from the electrons in atoms. These bonds are created by electromagnetic forces, the same type of force that exists between two magnets. Just as we saw earlier with the energy stored between two magnets, the energy stored in chemical bonds is also a form of potential energy. When fuel burns, the chemical bonds within the fuel break and new bonds form. During this process, some of the potential energy stored in these bonds is released in the form of heat. So if we look at it closely, we can see that the chemical energy stored in fuels is essentially potential energy. Now, when it comes to nuclear energy, instead of electrons, we deal with protons and neutrons within the nucleus. Unlike the electromagnetic forces that hold chemical bonds together, the forces at play within the nucleus are nuclear forces. The potential energy stored in the form of these nuclear forces is what gets released during nuclear fission and nuclear fusion. In short, most forms of energy that we are familiar with can be classified into one of two categories: kinetic energy or potential energy. Now let us talk about light. Light is the flow of photons, which are particles of energy. Therefore, it is generally categorized as kinetic energy. However, photons do not have mass. Strictly speaking, this means light cannot be considered purely kinetic energy. Even so, the effects that light produces on other objects are similar to the effects caused by objects with kinetic energy. For this reason, in many cases, the energy of light is treated as kinetic energy. Now let us take a look at the law of conservation of energy. For this, first, let us set aside the concept of friction for the time being. Imagine a universe where friction does not exist. We will come back to friction later. In almost every process in the universe, energy is being transferred from one form to another. As we discussed earlier, there are two main forms of energy: potential energy and kinetic energy. Most phenomena in the universe involve the transformation of one type of energy into the other. Whether it is the swinging of a pendulum or the burning of a star, energy undergoes such transformations. However, in none of these processes is energy ever created or destroyed. It merely changes from one form to another. For example, when we set a pendulum in motion, we give it kinetic energy. As the pendulum swings upward, its height increases, and this kinetic energy is gradually converted into potential energy. At the peak of its swing, its speed becomes zero, and all its energy is stored as potential energy. This potential energy then causes the pendulum to swing back down, converting back into kinetic energy. The pendulum crosses the center point and moves to the other side, where the process repeats. In this way, the pendulum continuously oscillates, converting kinetic energy into potential energy and vice versa. If there were no energy losses due to air resistance or friction at the pivot point, this pendulum would swing indefinitely. The energy we initially provided would never be lost. But we know that friction exists in the universe. When a pendulum swings, energy is lost due to air friction and friction at the pivot point. This is why a pendulum that has been set into motion eventually slows down and stops. In the case of a pendulum, this energy loss happens very slowly, which is why it continues to swing for a long time. However, in many other cases, energy loss happens much more quickly. For example, when we throw a ball, we give it kinetic energy. But when the ball hits the ground, a significant portion of that energy is absorbed by the ground. The remaining energy is lost due to friction as the ball rolls. Even though we may give more energy to the ball compared to the pendulum earlier, the ball comes to rest much sooner because it loses energy at a much faster rate. In all these examples, the primary factor responsible for the loss of energy is the force of friction. Earlier, we discussed that when we work against gravitational force or spring force, the work is converted into potential energy, which can be recovered later. However, when we work against frictional force, the work does not get stored as potential energy. As a result, we cannot recover that energy. For instance, when we push a heavy object along the ground, we are working against the frictional force between the object and the ground. It is true that we are doing work because the object moves, but that work is not stored as potential energy. Instead, the energy is converted into heat due to friction at the contact point. This heat dissipates into the atmosphere, which is why we cannot reuse it. Take the case of the ball we mentioned earlier. When the ball hits the ground, part of its energy is lost as sound, and another part is lost as heat due to friction as it rolls. This energy is not destroyed. It transforms into forms like sound and heat that eventually dissipate into the environment. Once this energy has dispersed into the atmosphere, it becomes unavailable for practical use. The principle that energy cannot be destroyed remains true. However, certain processes cause energy to disperse in ways that make it practically impossible to recover. In other words, some processes convert usable energy into unusable forms. While we can reduce the energy lost in such processes, we can never eliminate it entirely. This is precisely what the slogan "Save Energy" refers to: minimizing unnecessary energy losses and reducing the conversion of usable energy into irrecoverable forms. Now, let us explore how energy can have positive and negative values. For any parameter, whether it is positive or negative depends on where we set the zero point. For example, on the Celsius temperature scale, 0 is set at the freezing point of water. Temperatures below this are considered negative. However, on the Kelvin temperature scale, 0 is set at absolute zero, the point where molecular motion nearly ceases. Since temperatures cannot drop below absolute zero, the Kelvin scale has no negative values. But when it comes to energy, there is no such absolute zero. Energy is always relative. For instance, consider an object sitting on the surface of the Earth. If we take its potential energy at the surface as zero, then lifting the object increases its potential energy. Conversely, if we dig a pit and place the object in it, its potential energy decreases. Since we already defined zero at the surface, the potential energy of the object in the pit becomes negative. This is how the concept of negative energy arises. By convention, in gravitational systems, the potential energy of an object at infinity relative to Earth is taken as zero. With this reference, any object closer to Earth than infinity will always have negative gravitational potential energy. Now, let us address the question: where does the light in a room go when a bulb is turned off? When light from the bulb hits the walls and objects in the room, Not all of it is reflected. Some of the energy in the light is absorbed. This absorption slightly warms the walls of the room. When the bulb is on, this energy loss is continuously compensated. However, when the bulb is turned off, the remaining light in the room is quickly absorbed by the walls and objects. You might wonder, if the walls only absorb a small fraction of the light, how does the room go dark so quickly? The speed of light is 300,000 kilometers per second. Within a millisecond after the bulb is switched off, the remaining light in the room reflects thousands of times off the walls. Each time, a small fraction is absorbed, and within a very short time, all the light energy is absorbed. This is why the room does not retain any light after the bulb is turned off. Now let us talk about what happens to the energy in our body after we die. When we are alive, the cells in our body continuously produce energy. This energy is generated by using the nutrients we obtain from the food we eat. The energy produced by our cells is what powers our body. After we die, this energy production in our cells ceases. The heat energy present in the body at the time of death dissipates into the atmosphere. What remains is the chemical energy stored in various types of chemicals within our body. If the body is cremated, this chemical energy is released as heat and light during the process. On the other hand, if the body is buried, the energy in the form of chemical bonds becomes a source of nourishment for microorganisms and insects that consume the body. In either case, the energy is not destroyed. It simply gets transformed into other forms. Contrary to popular belief, the energy from our body does not wander around aimlessly after death. In everyday language, the word energy can have many meanings. There's nothing wrong with saying, "I feel positive energy" when talking to certain people, or "there is negative energy in this room." These are valid expressions in language. However, just because the word energy is used in these statements does not make them scientific. In science, the word energy has a very specific meaning. By this scientific definition, the use of the word energy in such statements is meaningless. If you enjoyed this video, please like and comment. Your support motivates me to create more content. Do not forget to subscribe to the channel and hit the bell icon to stay updated with new uploads. Thank you.